Whoa, whoa, whoa! This is Mr. Tran with another online video. Today, we will be talking about the gas laws. The objective is to describe and calculate relationships between volume, pressure, moles, and temperature of an ideal gas. The first relationship that we will define is between volume and pressure of a gas. Volume meaning how much space a gas takes up, and pressure is the number of collisions that are occurring between the gas molecules and the walls of the container. So Robert Boyle conducted different trials where he compared and measured the volume of a gas and its pressure. Now, we look at the 4 different trials that he has. I'm looking down at the trials, and as each trial progressed, it looks like he's increasing the volume. So I'm going to write up here as volume increases. That means there are more space available. If there's more space available, what should happen to the number of collisions between gas molecules in the walls of the container? So I'm taking a look at the pressure, and when my volume increased to 40, the pressure decreased to 0.251 atmospheres. It's considerably lower, so we can say as volume increases, pressure decreases. We call this an inversely related relationship. So inversely related. So I can take my volume and my pressure and multiply them as shown by the data table. And when I multiply these two numbers together, 10 and 1, we see that it remained the same. I take the others and multiply them as well, and it's all close to 10. I get the same answer every time. I can also fill in my graph as volume, or again, amount of space increases, the pressure decreases. So my line should be decreasing. We can summarize Boyle's law by saying that pressure and volume of a gas are inversely related. And I can replace related with proportional as well, and it will be the same thing. Inverse means opposites. When one goes up, the other goes down at constant mass and temperature. Volume increases, then pressure decreases. Same thing with if pressure increases, then we know volume decreases. We have our equation here, P1V1 equals P2V2. And again, that is Boyle's law. We have our first gas law problem. A gas occupies 100 milliliters at 150 kilopascal. Kilopascal, by the way, is just a unit of pressure. Find its volume at 200 kilopascal. Always, when we start a problem, always list your givens on the left-hand side. I always list in the order of the equation, but I list my ones first and my twos second. So the equation is P1V1. So I know that I need to list pressure first. So I see my first pressure. It is 150 kPa, kilopascal again. And my first volume is 100 milliliters. Again, the word at connects these two numbers. So they're my first set, my ones. Then it says find its volume at 200 kilopascals. So that's my P2, 200 kilopascal, and my volume is unknown. So now I take a look at the numbers and let's see what happens to them. With pressure, P1, P2, it looks like pressure increases. So using the properties we've learned from the previous slide, I do know that I should predict the volume to decrease. So it should be less than 100 milliliters. Now, after I have my listed givens, I move on to the equation. So I always write my formula first, P1V1 equals P2V2. Now I find the variable that I'm looking for and I try to isolate it. So V2 is paired up with P2. I don't want this P2 here, so I'm going to divide P2 on both sides, and that gets rid of P2. So I rearrange it so it looks nicer. 2 V2 equals P1 V1 over P2. Now that I have my desired variable isolated, I want to plug in. So I plug in my numbers. When I see P1, I put it in 150, and so on and so forth. Now I simply multiply and divide, and I get my answer. V2 is 75 milliliters. And it is indeed less than 100 milliliters, so that makes sense. The next set of variables that we will describe is volume and temperature. Volume is the amount of space. Temperature is a measure of the average kinetic energy or the motion of our particles. We can see here from Charles' data that at temperature of 273.2 Kelvin, the volume or the amount of space that the particle takes up is 40 milliliters. So again, this is the first two. So what happens if I increase the motion of those particles, or the average kinetic energy, to 348.2 Kelvin? If the molecules are moving faster, they're definitely going to take up more space, and I can definitely see that by looking at the number. It increased to 51.3 milliliters. This means that volume and temperature are directly related. So volume and temperature are directly related. Directly related means that if one goes up, the other one also goes up. So when volume goes up, temperature also goes up. But it also means if temperature goes down, then volume must go down as well. In this case, I can't multiply my two variables together and expect to get the same answer every time. I'm going to actually have to divide, and we can see that from the data table. I'm going to divide, and when I do that, again, it turns out to be approximately the same answer every single time, no matter how I change my variables. It increase and increase. So my graph here for temperature and volume, if I increase temperature, is also going to increase my volume. So it's going to be a line pointing up, a positive slope. To summarize this, the volume and temperature of a gas, we're going to say that they are directly proportional. That's the same thing as directly related, okay? And this occurs at constant mass and pressure. If volume increases, then we know temperature increases as well. And I have my equation, y'all. Charles' law is an equation as volume 1 divided by temperature 1 is equal to volume 2 divided by temperature 2. And just a quick way to get rid of the fraction, I simply cross multiply, and it is now in a neat line. V1T2 equals V2T1. Just a quick reminder, we will always use the Kelvin temperature when working with gases because if you notice over here, Fahrenheit and degrees Celsius both go negative, and I can't have negative numbers when I apply them to the combined gas law or the ideal gas law. Since I can't have negative volumes or negative pressures, we're always going to be using the Kelvin scale. Goes from 0 to 373. Just a reminder, we always add 273 to our temperature, degrees Celsius, in order to get Kelvin. Our problem. A gas occupies 473 centimeters cubed at 36 degrees Celsius. Find its volume at 94 degrees Celsius. Whoa, 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 let's stop and look at this. The unit is in degrees Celsius, but like I mentioned previously, we always have to use Kelvin. So in order to get degrees Celsius into Kelvin, I need to add 273, and I'm going to do that in my givens on the left-hand side. So I always list my givens from the order of the equation. So VT. V1 is 473 centimeters cubed, so there it is. The next one is T1, and I need to list it as Kelvin. I do this by adding 273, and I get 309 Kelvin. The volume is what I'm looking for, so I need to write down a question mark next to V2 to tell me that I'm looking for it. And finally, 94 degrees Celsius is simply 367 Kelvin after I add 273 to it. I have all of my givens listed now, and I'm going to see how the numbers change. So the only thing that changes temperature 1 to temperature 2, that's 309 to 367, so it increased. So with increase in temperature, I know that volume should increase as well. Next step, I need to write down my formula. V1T2 equals V2T1. Now, I'm looking for V2, so I need to get rid of this T1 by dividing both sides by T1. Okay, rewriting that in a very neat way, we have it here. So, after I have my desired variable isolated or by itself, I plug in my numbers from the given list. So V1 is 473, etc. I plug it in, and now I multiply and divide, and I get my answer to be volume 2 is equal to 562 centimeters cubed. And I note, just as a haha moment, that it is indeed bigger than 473. Gay-Lussac's law is going to describe the relationship between pressure, the number of collisions, and temperature, average kinetic energy of our molecules. Now, if I look at his data, it looks like as I increase the temperature I have here is 40, the pressure is 0.910 atmospheres. If I increase the energy or motion of those particles, and my temperature is now 51.3 Kelvin, it looks like my pressure also increased to 1.37 atmospheres. That makes sense if you are moving with more energy at a faster rate. The molecules would collide more frequently, so pressure and temperature are directly related. So pressure and temperature are directly related. This means when pressure goes up, temperature goes up as well, and vice versa. If pressure goes down, temperature will also go down. Our line here, when I graph the data, should be pointing up with a positive slope. The relationship between pressure and temperature of a gas is that they are directly proportional. So I'm going to fill that in, directly proportional. And this only occurs at constant mass and volume. If pressure increases, then I know that temperature increases. I have my equation, y'all, as P1 divided by T1, and that should equal P2 divided by T2. But since I don't like fractions, I'm going to be cross-multiplying it and making it into a nice, neat line. All multiplication here, P1 T2 equals P2 T1. So if you haven't noticed this yet, anytime our formula is containing a T is always going to be the opposite of whatever the variable is. So notice here, P1 is 1, so T is going to be the opposite, and that's 2. If we look at a practice problem, a gas pressure is 765 torr at 23 degrees Celsius. At what temperature will the pressure be 560 torr? I always list my givens first, again in the order of the formula. P then T, so P1 is 765 torr, that's P1. T1 is 23 degrees Celsius plus the 273 to get me 296 Kelvin. The second pressure is 560 torr, and I'm looking for the final temperature, T2. Now that I have all my givens listed, I'm going to compare the number change. So with pressure first, I see that pressure decreased from P1 to P2. So using Gay-Lussac's law, if pressure decreases, I know that temperature should decrease as well. So it should be less than 296 Kelvin. Showing my work now. Always list the equation or formula. Isolate the variable we want. So isolate means I need to get T2 by itself. So I need to divide both sides by P1. And again, erasing here to make it look nicer. So I have T2 by itself. Plug in the numbers. Numbers plugged in, calculate. Again, my answer is indeed 217 Kelvin. But if we subtract 273, we get negative 56 degrees Celsius. And again, I just did this process here to show you that we can get into Kelvin and also get out of Kelvin. But it's not a crucial step, y'all. You can stop at 217. Now we're going to combine all of our gas laws together. We said that Boyle's law is pressure and volume are inversely related or opposites. So if I take the pressure and volume and multiply those variables together, I get the same constant or the same answer. I'm going to call that K. It's just an arbitrary K. I can also take, according to Charles' law, volume and temperature, and because they are directly related, I can divide volume by temperature and get the same answer every time. And I'm also going to call it K. Then Gay-Lussac's law also says that pressure and temperature are directly related, so I'm going to divide my variables together and get this letter K. So we're going to combine all three of our variables, pressure, volume, and temperature, and see what happens. Okay, so we have right here, I'm going to show you guys all the laws. P and V multiplied together. We also have P divided by T, and we also have V divided by T. So all the three gas laws are combined. If we take a set of these conditions and label it 1, I can set them equal to the same set of conditions and call them 2, and that's what we see here. I can also get rid of the fraction by cross multiplying. And then when I do so, I get a nice neat line. P1V1 T2 equals P2V2 T1. And this right here, y'all, we call the combined gas law. A phrase that you are going to see is called STP, or standard temperature and pressure. Standard temperature is 0 degrees Celsius, also known as freezing. So again, this is standard temp. 0 degrees Celsius is definitely equal to 273 Kelvin. We will always use 273 Kelvin to represent standard temperature anytime we do gas calculations. Standard pressure is 1 atmospheres, which is equivalent to 101.32 kilopascal. We're going to try to focus on the atmospheres, this unit right here, atmospheres, but I do want you to know that 1 atmospheres is indeed equal to 101.32 kilopascal, and that right here, and I'm boxing it or circling it, is a conversion factor. So I can convert from atmospheres into kilopascal or from kilopascal into atmospheres using dimensional analysis. We are going to try one combined gas law problem just to make sure that you get it. A gas occupies 7.84 centimeters cubed at 71.8 kilopascal and 25 degrees Celsius. Find its volume at standard temperature and pressure, or aka STP. So once again, just like the previous gas law problems, we're going to be listing our givens on the left-hand side in the order of the equation. So it's PVT. PVT, easy. So pressure 1 is 71.8 kilopascal. Volume 1 is 7.84 centimeters cubed. And our temperature is in degrees Celsius. Change it by adding 273, and we get 298 Kelvin. Now, our second set, we're asking for volume. So we're looking for volume, and we're given STP. So at standard pressure, that's P2, standard pressure, I need to plug in a number that's given to us on the previous slide. But which unit do we use? We always use the same unit given in the problem. Even though I said we would try to focus on atmospheres, if they don't give us atmospheres, we can't use atmospheres. So they gave us kilopascal. We're going to be using standard pressure at kilopascal. So that's 101.32 kPa. Then V2 is what we're looking for, so a question mark, and standard temperature is T2. That is always going to be 273 Kelvin. Now we write our formula, P1V1T2 equals P2V2T1. I need to get V2 by itself. So I do that by dividing both sides by P2T1. And the nice rearranged form for y'all right there. So V2. Now that I have V2 by itself, I simply plug in my numbers. So plugging in my numbers, this should say V2. So plugging in my numbers, I multiply. Any number you guys see on the bottom, if you guys are wanting to type it in your calculator in one go without writing anything down, I would just simply multiply all the numbers on top. Then for the bottom numbers, I would push the divide button. So divide 101.32 and then divide 298. When we do that, we should get 5.09 centimeters cubed. And that is our answer, y'all. We talked about the kinetic molecular theory a while back. We said that, according to the kinetic molecular theory, gases are so small compared to the amount of space that they take up that we say they don't have any volume, and that there are no attractive forces between those gas molecules because they're so far apart. Well, real gases do have some of their own volume, even though it's very small. They do have volume though, and that there are some attractions between those gas molecules. In ideal gas, or a gas that would behave ideally, it will occur at low pressure. At low pressure means that there's not a lot of force pushing on those gas molecules together, which means that they can stay as far apart from one another as possible. Same with temperature. If I have a high temperature, it means that the molecules are moving very, very fast. They're moving so fast that they take up more space, and there are fewer attractive forces that can overtake those fast-moving molecules. Gases are also going to behave more ideally if they are nonpolar atoms or molecules. If they are nonpolar, that means there's no charges or slight charges on the ends of the molecules, which means there's less attractive forces between them. So a review of that kinetic molecular theory. Gases expand to fill any container. They have random, linear, adding that word there, linear motion, and no attractive forces. Gases are fluids. That means the molecules can flow one right over the other. And gases have very low density. If we take a look at the picture on the right-hand side, I can take a note that, again, the left hand is considered solid, very packed. The middle is considered to be liquid, and the right-hand side is considered to be gas. All of them represent the same volume or the same amount of space because the boxes represents that. And the right-hand side has the fewest molecules or the fewest amount of mass. So if we recall, density is mass divided by volume, and if all of these guys have the same volume, then their density depends on their mass. So since gases have less molecules or the fewest amount of mass, gases would be the least dense. Gases can also be compressed because there's so much empty space between the gas molecules. A great example is when you spray perfume and can smell it on the opposite side of the room. That means that the gas has diffused and filled the container, aka the room. Effusion is when a gas leaks out of a small hole. That's what you're seeing over here on the far right hand side. If I have a small opening in a container, effusion occurs when that gas is escaping from the small opening, and I'm going to highlight that there. So when we are considering the ideal gas law, the gas is behaving ideally, so it has no volume and no attractive forces. We are trying to figure out the relationship between pressure, volume, temperature, and now the number of moles of a gas. So now let's incorporate our number of moles using Avogadro's principle. Notice that we have three different gases that we are observing. The volume is all the same, 100 milliliter containers. Now, even though I have three completely different gases with completely different molar masses, oxygen having 32, nitrogen's molar mass being 28, and carbon dioxide being around 44. I look at these masses and there really isn't a significant difference in their masses or their moles. So again, masses, moles, no difference. Very, very similar. So it looks like I have different gases that occupy the same amount of volume. So volume and number of moles will be the same. As long as the volume is the same, the number of moles are going to be the same for my sample. Now, what happens if I increase the number of moles of a gas? Well, if I have more gas molecules, they're going to take up more space. So my relationship between the two would be directly related. If I have more volume, those moles will take up more space. So to summarize, equal volumes of gases contain equal numbers of moles at constant temperature and pressure. It's true for any gas. For the ideal gas law, we are going to include the letter N for the number of moles. N now represents the number of moles of gas. Because we said that volume and number of moles were directly related, notice that I have to divide those two values in order to get that same constant K. But we're going to change that constant letter to the letter R. We call this the universal gas constant. R is equal to 0.0821 atmospheres liters divided by moles Kelvin. We have a different value for R if it's in kilopascal, but we're going to focus on using this R here, using atmospheres for our pressure. If we move everything in a nice neat line, we get PV equals nRT. You will hear me call it the pervert law. Again, let's repeat that. Pervert law, not pervert, the pervert law. We can now solve for moles or grams of a gas using this law. As a reminder, y'all, we're going to try to use this R constant here, if possible. So we're going to break down the variables now. P is pressure, and it's measured preferably in atmospheres, or it could also be kilopascal. Volume is in liters. We have N is the amount of moles, or moles. R is the universal gas constant in atmospheres liters divided by moles Kelvin. And finally, temperature must always be in Kelvin, no exceptions. So, a quick example. Calculate the pressure in atmospheres of 0.412 moles of helium at 16 degrees Celsius and occupying 3.25 liters. As always, we list the givens on the left-hand side in the order of the equation per NERT. So P is first, and that's what we're looking for. V, N, R, T. And that degrees Celsius, we must convert to Kelvin by adding 273. Next, we list the equation or formula, NERT. We're solving for P, so I need to get P by itself. I simply divide both sides by V. That cancels that out, and I'm erasing this to show y'all the work. So it's P equals nRT divided by V. Now that I have P by itself, I need to plug in my numbers. Plugging it in, and so let's cross this out. Moles on top, moles on bottom, Kelvin on top, Kelvin on bottom, liters on top, liters on bottom. So the only unit left is atmospheres. So once I multiply and divide, I get my answer to be 3.01 atmospheres. Put a box around it. Another problem. Find the volume of 85 grams of oxygen gas at 25 degrees Celsius and 1.03 atmospheres. Again, list the given on the side in the order of the equation per NERT. So P, V, N, and again, we're going to see how we got that. Moles, R, T. So how did I get 2.7 moles? I need to convert my 85 grams of oxygen gas into moles of oxygen gas. So that's what we're going to do right here. So start off with 85 grams, plug in the bottom with the molar mass, on top is moles, and we get 2.7 moles. We list our equation or formula, PV equals nRT. We need to get V by itself, so I simply divide P on both sides. Now I have V by itself, plug in the numbers. Again, the fun crossing out of units to get the correct unit at the end, which is liters, and I have 64 liters as my answer. I have two more quick gas laws for you. Dalton's law of partial pressures and Graham's law of diffusion. We'll just briefly talk about those together. Dalton's law says that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual gases. So just like our current atmosphere, it is filled with many different types of gases. So that the total pressure that we record for atmospheric pressure, which is 1 atmospheres, is equal to the pressure of each individual gases. So again, atmospheric pressure is equal to the sum total of pressure of oxygen is in our atmosphere, carbon dioxide, nitrogen, hydrogen, and many other gases, and that's represented by the 3 dots. So if I want the total pressure in a container, I'm going to take the pressure of each individual gas in that container and add them together to get the overall pressure. We call that Dalton's law. Every gas exerts its own partial pressure. We performed a lab in which we collected oxygen gas over water in an inverted graduated cylinder. This lab right here is similar. Hydrogen gas is collected over water at 22.5 degrees Celsius. And we call that the atmospheric pressure within the container, and it contains the pressure of hydrogen gas and the water vapor gas. Find the pressure of the dry gas if atmospheric pressure is 94.4 kilopascal. Anytime you collect a gas over water, some of that gas that you collect is a water vapor that's being emitted by the water sitting in your graduated cylinder. We need to account for that. So to find the pressure of the dry gas, we need to use Dalton's law. Okay, so let's list out our givens. The atmospheric pressure is 94.4 kilopascal. Okay, and that's the pressure in the container. That's a mixture of both the hydrogen gas and the pressure from water vapor. We're looking for the pressure of hydrogen gas. And the pressure from the water vapor is given to us from a book. And this book is a very thick book, full of numbers. And for the number at 22.5 degrees Celsius, it is 2.72 kilopascal. So now, to show our work, we use the equation. Total pressure is equal to the partial pressure, or the sum of the partial pressure. To get pressure of hydrogen gas by itself, I need to subtract the pressure of the water vapor on both sides. And that's what we have here. Then I plug in my numbers and simply subtract. So the partial pressure of hydrogen gas is 91.7 kilopascal. Finally, we have Graham's law of diffusion. Diffusion is the spreading of gas molecules throughout a container until they're evenly distributed, whereas effusion is the passing of a gas molecule through a tiny opening in the container. Graham's law is all about how quickly molecules diffuse or effuse. A kinetic energy is determined by temperature, or rather, temperature is a measure of how quickly molecules are moving. So we already said that the higher the temperature, the faster the kinetic energy. So the molecules would diffuse faster at a high temperature. That should be a given, but what if my molecules are all the same temperature? They should have the same kinetic energy, right? We know that some gas molecules are larger than others. For example, we have hydrogen gas and it's really, really small compared to oxygen gas. We have these two gases at the same temperature. Which one will diffuse or effuse faster? Graham's law says that the heavier molecules move more slowly, and that's based on the formula for kinetic energy. Kinetic energy is equal to 1/2 mass times velocity squared. Again, this equation just reinforces the concept that bigger things move slower. So to answer the question, oxygen would move slower while hydrogen gas would be faster just because of the mass alone. It's physics. So to end the day, I'm going to give you guys a reminder of this cute baby horse running with little legs video you guys can check out on YouTube, or you can find it in our PowerPoint, but it couldn't play it with the recording and export it as a video. Sorry. Anyways, hope you guys have a good one.